and one day we hope to replace it with little penguin insides. Ladies and gentlemen, I present to you Mr. Ron Minich.
Oh, now is the microphone working? Okay. I wanted to thank FOSDEM for having me here, and obviously it talks about LinuxBios. Now, sometimes people ask you what you're going to talk about, and then you send them a paragraph, and the paragraph is in your program, and I realize this talk bears some small resemblance to that paragraph, but it's not actually the same thing. So I'm just going to talk about what it is, why we're doing it, give you some idea how it works, and then talk about what the Google-supported work is all about, and then where we're going to go with it. So what it is really exactly what it says it is. The plan starting 8 years ago was that Linux would be your BIOS. And, you know, we mean it, right? So we're going to take Linux completely out of the flash, put Linux into flash, throw the PC BIOS away. How many people here like the PC BIOS anyway, right? I hope no one's going to raise their hand, right? We all hate its guts. So the goal here is to get rid of the PC BIOS completely. It's a 1981 piece of technology. Who needs it, right? And in theory, it should be easy, as Jim mentioned this morning. You know, these computers are actually fast. It's just all that our software makes it feel slow. So, you know, getting Linux running in a few seconds is really something that is pretty simple to do. Who uses it? Here's a couple of supercomputers that use it. There are about 8,000 various types of computers at LAML that run Linux BIOS. This is the Cray XD1. Cray has been using it for some time. This is, of course, the OLPC, the iRobot PackBot. That's kind of a neat application. That thing actually is kind of a mine detector, and the thing you know is every time one of them gets blown up, it means some human being didn't get blown up. So that's kind of a nice application. This is kind of neat. This is an FPGA card that plugs into a hypertransport socket. So there are several companies now that take a dual Opteron motherboard, take one Opteron out, and put an FPGA in, or that have a card like that. That card was designed at Mannheim. Well, what happened when Extreme Data tried to do that? They got a Sun Ultra 40 dual Opteron machine. They took one Opteron out, and the machine would not boot anymore, right? So the super duper proprietary BIOS was too dumb to boot the machine with one processor removed. So I did a port last summer of Linux BIOS to that machine, and it comes up just fine with Linux BIOS. But the other really neat thing is it turns out, according to AMD, that the code in Linux BIOS that turns on hypertransport is better than any proprietary BIOS in existence. You get the open source BIOS, you're not going to get the proprietary BIOS. That's kind of neat, right? So we're really at the point where we're doing a better job than the closed source junk. So how many people use it? So this is kind of funny. We bought a 1,000-node cluster here, and we thought we'd kind of hit the big time with Linux BIOS. But compared to where we're going, and I mean, it literally is a growth of 10. So that year we had 1, then 10, well, no, I'm sorry, 10, then 100, then 1,000, and you know, it's a 10x growth every year. And you don't really realize what that means until you get about to here. Then you realize a 10x growth a year kind of adds up after a while. So, you know, but the funny thing is, you know, the point here where we thought we hit the big time isn't even visible in this graph. Why would you bother, right? Why would you bother using Linux as a BIOS? So the motivation for me is this column right here, drivers. So you can use something like EFI, which is proprietary, as we all know. That's Intel's BIOS that they're trying to get everyone to use. Yes, it's extensible. You can do it in C, but the way you extend it is you get the 1,500-page EFI spec, attempt to understand it, which I can't yet. It's a totally new API, new programming environment. You need a special GCC. You've got a DOS-like file system, okay? You've got to live in that weird environment with a DOS-like command prompt and do a full custom driver. Or you've got open firmware, which is a lot better. It was proprietary. It is no longer proprietary. It is extensible, but you've got to figure out how to write these drivers in Forth. Okay, some people can do that well. I can't. There's the PC BIOS, proprietary, but you know, if you're good at assembly, you've got it made, right? So all you good assembly language programmers out there, you're set. I don't really like writing in assembly. The big thing here is, you know, Linux, if it's my BIOS, it's not proprietary, it is extensible, and we all know how to do that stuff, right? It's a driver. And most of the time, somebody else writes the driver for you, so you don't even have to think about it. So, you know, do you like writing non-Linux drivers when working Linux drivers exist? I think all of us would just as soon use someone else's driver. Or this is the fun one. You know, you have a piece of hardware that works fine in Linux and fails in the BIOS. That gets really old really fast. Or if you write a driver for one of the first three, guess who gets to maintain it forever? And this is a nice thing. You know, we've been working on getting some of our code into Linux kernel. The neat thing is you're on a mailing list and you start seeing patches come in from all over the world to fix bugs in your stuff that you submitted. So it's a lot simpler and a lot cheaper to have the same drivers in the BIOS and in the OS. And that's part of the argument for having Linux as your BIOS. I should mention the DRM BIOS issue. This is a funny phrase. It was coined by a guy I know at Google. We were talking about Linux BIOS, and he said, well, you know, Intel EFI is just a DRM BIOS. And we talked a little more about it, and here's the thing. The newer BIOSes have unlimited control of your memory and I/O cycles. What's that mean? What that means is that in the chipsets that ship in all your machines out there nowadays, the BIOS can set a bit and set an address range, and any I/O you do in a certain address range will get trapped to a system memory management node handler. At that point, the BIOS can decide to veto your I/O. What's really fun is they also implement a full network stack, okay? So, you know, how paranoid do you want to get? It is actually in the range of possibility that the BIOS could look at the kinds of things you're writing to disk from the operating system using the IDE I/O ports, and the BIOS might get upset about the kind of data you're writing to the disk and send network packets somewhere. It's all possible. It's all possible today. How do you know what it's doing? You don't and you can't by design. So that's a little worrisome, right? I've known some people at some banks that are very upset about this because what they've realized is they may be running Linux, but they don't know what's happening underneath. We had a long telecom with Intel about this, and they were explaining the really cool aspects of EFI, the fact that things could get intercepted and EFI could take action for us. And in fact, EFI could go out, find a server, download a new version of EFI, and burn it to flash, all without us knowing or intervening. And, you know, panic ensued at the end of that conference call because we had just been told that the BIOS was kind of able to go off and do things without any direction from us. So what we've required for the last 6 years when we buy a supercomputer, it either run Linux BIOS or more recently, they have to give us full and buildable BIOS source because it turned out IBM didn't want to let us run Linux BIOS. So what IBM did on the most recent machine we bought, they shipped us buildable BIOS source for that machine, which I'm never going to look at because I don't want to get contaminated. But you know, this is the way we work, and we did it for security reasons. You know, BIOSes that can take action on their own are really a bad deal. More people should be worried about them than are worried about them. Linux isn't a BIOS only, though. It's a bootloader, too, right? Since Linux can mount and use all the Linux file systems, it can do everything you need done. It can do the KExec, it can mount things, it's got network protocol stacks, it's got all the drivers you need to get the things. So Linux is actually a great bootstrap loader. What if you need a new file system? Well, it's always there in Linux. Do you really want to write a whole new set of file systems in the EFI environment that are enforced? And again, I don't. Somebody already wrote them. They're already in Linux. I don't need to do that again. So if you remember all those custom entries for drivers, we've got the same entries for file systems, network file systems, network protocols, wireless, you know, the list goes on and on. It's a long list. So the way we use Linux is Linux as BIOS and Linux as bootloader. We've measured this. It's the most reliable and flexible and fastest way to boot your machine. This is interesting. Until about 3 or 4 years ago, Etherboot was always a really fast way to boot a machine. And if we put Linux in Flash and Etherboot in Flash, Etherboot was always a little bit faster than Linux. At some point, when the CPUs hit about 2 gigahertz, we discovered that Linux was always faster than Etherboot. And It's not that intuitive. Etherboot is this sort of direct, small kernel, polling I/O. You'd sort of intuitively think, okay, Etherboot has less overhead than Linux, it'll be faster. But what in fact happens is Linux has so much internal concurrency and overlapping of operations, it's actually the fastest bootstrap we've used. And the other fun part is, of course, these non-Linux systems tend to fail in unforeseeable and unpleasant ways, okay? And I have a friend who has 4,000 node cluster. And they came in one day and every single one of the 4,000 nodes was hung. So they went up to one node and found out that the node had said, no keyboard present, hit F1 to continue. It turns out you can fix the problem in parallel. The parallelism is limited by either the number of people you have or the number of keyboards you have, okay? So if you can imagine 20 people fanning out, walking up to machines, bam, F1, bam, F1, bam, F1. It only takes a couple hours. So, and I'm not allowed to name the lab or the company because they're so embarrassed about it, even though it's been almost a year since it happened. What do you want to see if things go wrong? Now, a lot of BIOSes will do something really friendly like this. This is my favorite, actually. Can't boot disk, okay. And, my reaction is, what is okay about this? I've never known why it's telling me things are okay, because they're really not okay. And in fact, this is even worse than hit F1 to continue, because if I know about F1, I hit F1. What am I going to do here? I've got to interact with this thing. In a supercomputer cluster, this is about the worst possible thing you can ever have happen. There are a few things worse than the OK prompt in a cluster. What you really want the node to do is always go over the network and talk to you over the network about what's going on, right? A lot of companies, and I'll just say the generic big search engine company don't even hook consoles up to their clusters. I don't either, right? It's been years since I hooked up the consoles on a cluster. That's what the network is for. But what do you want to see if things fail? Well, if I have to have something that's going to give me this awful prompt, it really should give it to me over the network. But I want a shell prompt. I want a Linux shell prompt. I want BusyBox binaries, right? I don't want this. I really don't want that. I had it for years on SPARC stations. That was enough. What if you want to extend the BIOS? Do you need to extend the BIOS temporarily for debugging purposes? Real easy on Linux, right? Mount a disk or a network file system, change your path, insert a module, whatever you want to do. Knock yourself out. It's Linux, okay? So you can trivially extend your BIOS, if Linux is your BIOS, with new commands and modules and whatever you want to do. That's just really not easy with a standard BIOS. Sometimes you don't have any other options, so anybody who's got the new Intel chipset will find there's a new feature on that chipset. It's on that laptop which Stefan loaned me. It's called the regulatory daemon. Has anyone seen this thing? You cannot run that wireless card without the regulatory daemon. You can only get it as a binary. Yeah. You can now? Thank God. Okay. So there is a way out of this hell. That's good to hear. Nevertheless, if you need a WPA supplicant, or if you're running something really complicated like InfiniBand, that gets a little messy, right, in something like EFI or open firmware. And at some point, should the BIOS or the bootloader have modules and processes? Some people say, yeah, but at some point you're just building a bad OS. Why have a bad OS as your BIOS when you can have Linux? There's no reason to recreate bad OSs at this point. We've got a good OS. We know it can fit in Flash. Problem solved. So for the future and more complex BIOSes, I feel Linux wins again. The newer drivers are getting really complicated. Turns out we need one less binary component than I thought, but still, what's happening is as people try and stretch the BIOS to fit the hardware and the other things that are coming down the pike, they're turning into bad OSs. And EFI is just a great example. If you got your wireless up, go to openefi.org, download the 5 megabytes of that spec. realize at some point that it looks like a 1960s era operating system and just think, why the hell are we doing this? I actually don't know. So what we say is go with a simple BIOS idea. Linux is BIOS, Linux is bootloader. Okay, how does this work? And this is where the real fun begins. This is kind of a summary of some of what we've learned over 8 years of trying to make this thing go. First step is you've got to enable and bug fix the CPUs. Now, if CPUs is plural, I'll get onto this, but you've got to enable and bug fix the CPUs and then very quickly stop all but one. For hardware, you've got to discover, configure, and enable it. Pre-PCI, you really couldn't do this stuff, right? You had things like ISA, you had funky, little ROMs and stuff that had configuration information, but once we got PCI and we got self-configuring, self-defining hardware, life got less impossible, right? I won't claim that PCI is easy even now, but it's pretty straightforward. As an aside, I'd like to say I think OS is, our original thought and hope was that the OS, especially when 2.4 came along, the OS could configure all the hardware with no help from firmware. That has not actually proven to be true. I don't know if we're ever going to escape the need to have the firmware do a lot of pre-work for Linux before Linux and the other OSs can figure out what has to happen. What's the boot software have to do? They've got to pick a device. That you can do in a Linux RC. You can do further configuration. Again, this is boot software running out of firmware, out of flash ROM. Ifconfig, sfdisk, or whatever. Find a boot file name or location. Well, that's DHCP, or mount an equivalent and get some more information on a disk. Maybe do a mount, validate it, that's a file command. Boot it, that's kexec. So this is kind of the steps of a bootloader. Everything is there in Linux you need to do that. And we actually demonstrated that on OLPC. So before OLPC went to open firmware, the way it actually worked is it came up, we had BusyBox in Flash, that was in the initRD, or initramfs in some versions. We had the kernel in Flash. It came up, it had a Linux RC, it had a timeout, it would look around and see what was there, optionally boot something over a network or from a local flash. So, the system I delivered to Extreme Data, which again was a Sun Ultra 40, that also did the same trick. It came up with an ASH prompt and you could run a script to tell it what to boot. So if you know how to make Linux do things, you know how to make Linux as a BIOS do things. So the initial key idea was we thought Linux could do everything, save for the lowest level hardware. So this is the first version of Linux BIOS. It's pretty simple. It's 4 lines of code, okay? And it works like this. I hope I'm not going to move too fast. Mem copy jump. So that's Linux BIOS version 0. And it didn't work at all. And it didn't have a prayer working, as it turned out. And the first problem was what I call the DRAM problem. So here's a DRAM module. And I don't know how many people know this, but of course the DRAM module has a DRAM. But the thing that's on the DRAM module that's not always apparent is there's this serial EEPROM. Okay, why is there a serial EEPROM on a DRAM module? Well, here's the path you're used to. CPU to North Bridge to SDRAM bus to DRAM. That's pretty straightforward. Here's a path that not a lot of people are used to. CPU to North Bridge to South Bridge to Super I/O in some cases, or over here to the SM bus to the serial EEPROM. Okay, why are we doing that? The reason you do that is that DRAM module is a synchronous clocked machine. Okay, so there's actually a state machine here that communicates with the state machine here for memory cycles. Well, there's timing in these state machines. And the serial EEPROM defines the timing in the cases which are common that it's correct, but it defines the timing for this module. And so what you've got to do is configure up that bus all the way down, turn the Super I/O on, or Southbridge SM bus hardware on, talk to this, read the values in, compute from those values and your knowledge of the Northbridge timing how to set up the Northbridge. Well, what's interesting is you've got to do that with no stack. So you have no C function calls until you have DRAM. And you have no DRAM until you do all that work. So you've got to do all this stuff, do I/O over the I2C. You've got maybe 17 fairly complicated parameters. All of them interact. It's like having 17 springs that you can stretch, okay? And then you've got to match them to the north bridge. So some of the strings you got to make sure you don't stretch them too far because then the timing won't match. Then you have to program the DRAM and program the north bridge. So that code is the single hardest piece of Linux BIOS. And to give you an idea how messy it can get, we had a project to do port of this to the G5 and we never got it because there were some bugs in the G5 chipset that we weren't told about. So this code, though, is just about the hardest thing there is to do on any machine. And it's actually getting harder as time goes by. If anybody knows about DRAM training and the new DRAMs, you actually kind of sit there and you actually train it. It essentially tunes the delay lines. There's a delay line for every bit that goes out to DRAM, and that all have to be tuned slightly differently. So, and then there's a little bit more we have to do. So it ends up looking a lot like this. And some of these are empty on some things. You knit the display, you set the PCI method, there's methods 1 and 2. You manage the Super I/O. You really want serial output as soon as you can possibly get it because it just makes your life a lot easier when you're debugging. Then you enumerate PCI, turn the frame buffer on, but you can't really do this until you have some idea what the structure of PCI is. Then you enable PCI, initialize the CPUs, and then this is essentially that mem copy, more or less, that I showed you earlier. So there's a fair amount of work to do here, and in fact, some of this PCI code was ripped right out of 2.4.0. That's where we got it. Modified it quite a bit, but that's where that initially came from. SMP support is part of the let Linux do it philosophy. We actually had a guy who in 2000 wrote SMP startup code that ran in Linux. So the idea was your motherboard had come up and Linux kind of thought it was on a single processor board, but it would do a little looking around and figure out that it in fact was on a multi-processor board and start up all the other attached processors with the standard IPI mechanism and all that. What was kind of neat about this is that nobody had SMP startup code in C. It was all hidden in the BIOS as an assembly. So we finally were able to create this code and have a reference essentially for how to bring up an SMP, which was really nice to have. Then we got to the K7, and here's my theory, okay? On Pentium SMPs, there's hardware voting that goes on. So they all come up and there's some kind of hardware voting mechanism and they all stop except one. So there's probably a patent on that, speaking of patents. And so on the K7 it turned out there was no hardware voting. They all just came up and started running. And so we actually had to put the voting in software in the BIOS because we didn't want them all running the BIOS at the same time. And that meant that we had to take that code that we had started to put in the Linux kernel and make it descend down into very early code in Linux. I mean, in Linux BIOS, in fact, assembly code. So there's sort of this, for K7s, this sort of initial early vote step for who gets to run the BIOS in that. What that really means, it's an SMP BIOS. Now, at the time, I kind of thought, well, an SMP BIOS seems like a fairly useless piece of software, but then the Opterons came along. Every Opteron has memory attached to every Opteron CPU. You can now do memory initialization in parallel on Opterons. So the memory init in an Opteron is SMP on Linux BIOS. So that was all going really well. We had gotten to the point. Things were okay. We had 0.5 MB flash. 2.2 just fit right in there, no problem. But this became a big problem. And Jim alluded to this morning. Why is OLPC running open firmware when our initial efforts were all Linux as bootloader? Linux got too big, and it continues to get too big. And, it's been a problem, and to compound the problem, motherboards went to a new form factor. They went from the nice big DIP parts, okay, that seemed to have about 0.5 meg easily available, to these little small parts that at the time were just 1/4 meg parts. They were limited by pins. So at the same time, this guy was getting a little big, the flash parts were shrinking, so we kind of had to change things a little. So this was the vision in '99, right? This little Linux loader and Linux kernel, that's Linux BIOS. This is what it meant in 2002. Well, the simple payload loader is now called LinuxBios. We're doing things like loading Plan 9 kernels and Plan 9 loaders, and Philo, which is grub without BIOS calls, memtest, Linux kernels, and Etherboot, right? So this changed a lot. I'm from New Mexico. We've got this T-shirt. The T-shirt says New Mexico. It isn't new, and it isn't Mexico. So I told Stefan about that, and he said, well, this isn't Linux, and it isn't a BIOS, because we don't support callbacks. But, we've got the name LinuxBios, and it's kind of stuck. And it does incorporate chunks of Linux kernel code, so I guess we can stick with the name. But in 2006, we're actually getting back to where we began. So I mentioned that as little square flash parts that only hold 1/4 meg because they're pin limited. The newer parts are called LPC, and what they do is they multiplex the address in chunks. So you can get a big memory address that just sends it a bit at a time. And, the 2 megabyte part is not a big deal. 16 megabyte part is not a big deal. I saw this headline in an electronics newspaper recently, NAND flash is free. So the parts are getting big again, and, we know we can easily fit a kernel in a busy box, a lot of busy box, in 2 megabytes. That's not a big deal. And what we found when I talk to vendors and say, I can give you a couple of choices. We can put a grub-like thing in there. We can put an open firmware thing in there. We can put a Linux kernel in there with a shell prompt. Response is always the same. We want Linux. People want Linux in the BIOS. It's just the easiest thing for them to deal with. Then the next question they ask is it working? So that's where the Google work comes in. Google offered to support us with some money, which is always nice. And so Stefan Reiner, our core systems, decided one of the things we could do is build this quality assurance system. Why do we need it? Well, what happens with commercial BIOSes when they go to a new motherboard is they essentially fork the BIOS. So you've got this code base. This is what I've been told. And the commercial BIOS company will take their BIOS and send it off to someone, and at that point it's a fork. So the BIOSes are always forking. We don't do that in LinuxBios. We maintain a common code repository. But what that means is that as people do things and change things, at any given time we may have a motherboard that's not working. And we'd like to know that as soon as we can. But we can't afford to keep every single motherboard that's supported in-house. So what we needed is a way to have sort of distributed systems that report to a central system that we can test out new versions of LinuxBios on. So I'm not going to really talk about this much. This is kind of a rough view of the test cycle, but a lot of times what kicks this thing off is a commit from someone. And the first thing kicked off by the commit is a complete build of every single LinuxBios target. So that's part of what goes on. If any build fails, then an email gets sent out to the LinuxBios list saying this thing just broke. The test setup, so there's an automatic build system run by this test server. The test server in turn can control motherboards up to 16. And basically the test server can reflash the flash on that motherboard and then run it and look at the serial output and test it and see if the thing came back up. Now the neat thing here is every once in a while you'll flash a bad BIOS, and the potential is to turn the motherboard into a brick at that point, right? When you flash a bad BIOS, the motherboard's gone. But the hardware that Stefan set up allows us to recover from that, because there's actually 2 flash parts, sort of the flash part you can fall back to if you've really messed things up and recover. So we start with, the LinuxBios tree. We do a full A build. For the A builds to succeed, we control those motherboards, and then, do the testing and see if it works on a given board. So this is kind of neat. This is called a BIOS savior, which unfortunately you can't buy anymore. So we're going to have to solve that problem. This plugs in. There's a little tiny flash card here. This is the part you reprogram and potentially program with a bad BIOS. And under here is the one you recover from. And this little USB module essentially electronically controls the switch that flips between the two. So that's how you can take a chance where you might brick a board and still recover from totally trashing the flash part, right? Being able to get the board back. So here would be the central repository at openbios.org. These would be different vendors, right? So here's a vendor. This guy runs 2 systems under test. These are different guys running multiple systems under test and so on. So the idea is that we can have MSI and tie-in and other vendors set up these things, centralize the reports, and make them accessible to everyone. I don't think anything like this has existed before for BIOSes, because the vendors tend not to care if an older board or someone else's board fails. But we have a lot of cases now where this vendor will find a problem in a chip, and that will actually fix this vendor's problem. And we're kind of hoping the vendors are going to pick up on the fact that they're really somewhat in the same boat here, that they can actually benefit from each other's knowledge of, say, the NVIDIA CK804, the ins and outs of that chip, and if you fix it for one, you fix it for all. It is sort of happening. MSI has a full-time LinuxBios person now, and so does AMD. So people are kind of picking up that this is exactly the Linux dynamic here, right, applied to the BIOS. So these BIOSes images are built by the AutoBuild tool, and then we've got these daily snapshots of the images. This is kind of neat. I like this. I'm terrible at this, but Stefan's very good at it. So you can see that we've got a test name here. It's very hard to read, but this says banner, copy to RAM, jumping to LinuxBios, LinuxBios and RAM, and so on. And this is pass, failed. So you can see your SVN rev number, the target board, the failed and passed, right? You get a really nice test summary. And the idea here is, say MSI might only have 2 or 3 of these pages they're monitoring, but they can see very quickly overnight if something has happened. And they will get an email kicked off to them when a commit happens and anything goes wrong. So Stefan built this thing. He's using Deja GNU. This is kind of nice, right? You can really test it all the way up to Linux timer interrupts and do your IDE drives work and that kind of thing. So it's a really good assurance that you've probably got things right. It's kind of interesting, but if you've messed up the interrupt tables, this is often the first thing you see, right? It sort of says, I always forget the message, calculating BOGO MIPS or something, and then it never comes back. That means timer interrupt is just gone. So, I don't know if this applies to anyone here, but, Core Systems is looking for people to join in with this thing. So the future work, what I've talked about here is version 2. What happened was the very early thing was version 1, and the Opteron came in, and the Opteron was so complex and so far beyond what we were used to, because every Opteron essentially had 3 processor buses, which we weren't prepared for. A number of things came along and kicked off version 2. So version 2 ended up being very complex to deal with systems like the Opteron. What we're doing with version 3, now that we kind of know how it's got to look, is restructuring the code. And, it's for casual users, but it doesn't really mean, guys who just run AVI Word. It's kind of casual BIOS users. What we're really talking about is an engineer who might spend 1 day every 2 weeks working with this software. Doesn't have time to really learn it in depth, but wants to use it. So that's what version 3 is oriented to. We've moved to kconfig. That we hope will make a more familiar environment for people. We've greatly simplified the code pass because after a couple of years, you may have a lot of flexibility in how you construct an assembly code file, but if every component of that file is not changing more than about every 3 years, there's no reason not to just put it all in line in one file, right? It's just, we had complaints about the amount of usage of include. People don't generally like includes. Load scripts. We had made use of load scripts after the manner of the kernel, but I think we were doing a little more with load scripts than people are used to. So we kept tickling bugs in the GNU bin utils. It just seemed like we did that about once a year or twice a year. You'd start building images and they wouldn't boot at all, and you'd trace it all the way back and find out, well, GNU LD GCZ is generating new segment names, or GNU LD is somehow not doing the right thing. So we're really minimizing our use of features of GNU LD. We actually had a C compiler in the tree, and that was done to minimize the assembly code. This was written by Eric Biederman. ROMCC was quite a trick because what it actually did is it could compile a ANSI standard C program in a way that it used no memory. So It's 25,000 lines in one file, optimizing C compiler, complete with bugs. There are a couple bugs. It was really an incredible piece of work because you basically could tell it, oh, you're on a Pentium whatever, use MMX registers, or you're on this, use streaming SIMD registers or whatever. And it would basically use the registers and nothing else, right? And that's what you've got to do in that early step where RAM is not up. So you could actually write C code and compile it, and then you'd have this assembly that used no memory. But the problem was that that's a big maintenance effort, and we've learned how to use a newer or better thing called caches RAM. And basically on the Pentiums and PowerPCs and just about everything nowadays, you can pretty much play this little trick and all of a sudden the cache memory is kind of acting like RAM for some period of time. So we're moving to all caches RAM, and that means the only C compiler will be GCC. And we'll still have very minimal amount of assembly code. There's about 100 lines of assembly code in a given Linux BIOS. And politics. So you can't escape politics when the opposition to what you're doing is non-technical. You know, I don't know, we started this project and we thought that the benefits were so obvious that after a year we'd get companies in working with us. But what actually tends to happen is you get a lot of opposition because you're pretty much telling the BIOS vendors they can all go out of business now. And you're kind of telling Intel, we'd really like you to continue to release documents about chipsets, which they don't release anymore, by the way. So what's happened in the last 8 years? Anyone knows about developer.intel.com. I mean, the 440LX chipset, you pull the documents down, there was a tutorial in that document about how to program SDRAM, okay? 3 years later, the newer chipsets, there was nothing in those books about how to program SDRAM. And in fact, there are notes about there are certain registers we're just not going to tell you about unless you get an NDA. So, you know, once we started using the information that was posted, the information, in the case of some vendors, just vanished. So we kind of have to, you know, deal with this political stuff. The other thing is we're really trying to show vendors they can make money even if they let us do Linux BIOS. And the cool thing that just happened about 3 weeks ago is NVIDIA let AMD release all the programming information needed to do the Linux BIOS port for the NVIDIA chipsets. That covered 4 vendors. So there was an MSI, a Gigabyte, a Tyan, and a Supermicro motherboard using this particular chipset. So about the same week, probably the same hour for all I know, that NVIDIA okayed the release, Yinghai Liu at AMD released Linux BIOS for all these boards. It was just a wonderful day. The discussions with NVIDIA began from my end in 2002. And what they told us is, tell us how many million chips you will increase our sales by in a year, and we will release that information. So, you know, if we can show vendors there's a business case, and that's what happened with OLPC, right? Then they'll be on board. So, you know, you can't really demonize them, but they can be very frustrating people to deal with sometimes. And of course, continue to evangelize. So a lot of people maybe remember the IBM PC. It came out and a BIOS listing was part of the package you got. There was like this sheet of paper that was the BIOS, okay? And what people didn't realize, yeah, it was closed source, it was copyrighted. People had to do clean room re-engineering of the BIOS. So what we've shown is the highest quality BIOS can be built using free software. And it really is a good BIOS. It was interesting to have AMD tell us in an open meeting that the hypertransport software in Linux BIOS was better than their hypertransport software, and in addition, better than anybody's hypertransport software. That was just a shock, but we've seen other cases. It's so hard to set up DRAM that a lot of times what the BIOS vendors do is they don't do a very good job. So you get fast DRAM, they run it just slow because they don't want to deal with what a mess it is. So, you know, we found in a lot of cases we do a better job of programming DRAM than the proprietary BIOSes. We've hit the millions mark about a year ago. It's in a lot of systems you and we have never heard of. I get a phone call once in a while and somebody says, I mean, one of the ones I got was really funny. There's a television set made in Turkey. And they make 15,000 of these things. I forget if it's a month or whatever. And it's digital. And they found out that when they ran it with a PC and people turned it on, they didn't like waiting 90 seconds for the image to come up. So they put LinuxBios in it, and then the image came up in a couple of seconds, and then people were no longer angry with them. So, you know, I mean, it's just weird things come out from nowhere about usage of this stuff. One of the great remaining things is to get it in your laptop, and we don't know how to do that right now, okay? There was a DARPA project funded a couple of years ago. DARPA gave IBM money to put LinuxBios in a laptop. We were working with them. And the part of IBM that did laptops did not want to tell the part of IBM that got this money how to do it. They told them to go pound sand. So, you know, IBM isn't always very friendly to IBM. Of course, the laptop part of IBM got sold, so maybe there's some justice there. But, you know, it would have been nice to get that done. It would have been really cool. So if anybody has clever ideas about who we can talk to or how we can get this in a laptop, we're willing to listen and talk. So let me just show you one more thing, if I can. This was pretty exciting. First off, we don't know the guy who posted this. So this is just an announcement. First desktop motherboard supported by LinuxBios, gigabyte, blah, blah, blah. But what was really cool is, you know, AMD essentially said, we're supporting this. And this is where we've been trying to get for 8 years now, right? Is get to the point where someone at the level of AMD and Gigabyte would say, we're supporting this. Now, where we're not, okay, notice this is like a part number, right? But that part number means, I don't know, Phoenix or something, okay? What we wanted to have is M57 SLI-S4-LB, right? We want it to be the case that you go to Newegg or something and you order this part and it comes and LinuxBios is on it. That's the next hurdle. But actually getting AMD, I mean, AMD has just been great for 2 years now. They've just been absolutely incredible. But you know, having AMD sort of say, oh yeah, we hired this guy, he does nothing but LinuxBios full time, and by the way, we're releasing support for 4 motherboards. That was actually a really big deal. And that was just February 22nd of this year. So I guess that's it. Do we have time for questions, or did I run over? Okay. Or we can all go get coffee.
Hi. Oh. Will it boot my operating system of choice, e.g. OpenSolaris or...
Whoa, I didn't hear that.
Sorry. Will it boot up other OSs like OpenSolaris once it's done all the hardware initialization?
What was the first part?
Sorry. Will it boot any OS I like?
Oh, okay, so there are problems with different OSs. So years ago I tried to do FreeBSD because I'm used to do FreeBSD a lot. FreeBSD still wants to make BIOS calls. If your OS makes BIOS calls, you're out of luck. Your OS shouldn't make BIOS calls. It's a bad idea, but some of them do. I'm sorry? Somebody told me they'd done it. Okay. The OpenSolaris guys are here. Oh, we could walk on down and say, hey, do you guys make BIOS calls or not? If they say no, and the other thing we can do, you know, I've got it running in emulation on QEMU, we can just do it. Just test it and see what happens. So that would be kind of interesting.
About the last question.
What's this?
About
Windows? Windows, we actually had Windows booting under box BIOS years ago, but it was pretty painful. What we'd like to do is find the ReactOS guy again and have him talk to us about Freeloader. So, is that what you were asking?
no, that was just a secondary thing. But will this, in theory, do you need to do some hardware change? Do you need to do some hardware changes to motherboards to be able to run LinuxBios, or
No.
is the software flash?
No, you just reflash the flash and you can do that in place. We actually have a program called FlashROM that lets you do it. So from the web page, you can see from long ago, I used to add one address line for making the flash parts bigger, but I haven't done that for years. So, yeah.
Yeah, I'm using some clusters and I'm I like the idea of the LinuxBios project. So what's the getting started manual I can get for making my system compatible with your list? Today you have a list of hardware that is working with LinuxBios. How can I help you to having some more system available? Meaning, how can I help you to make my system working with LinuxBios? What should I need to start?
You should send mail to me.
Sorry?
You want to know how to make it work with your system? I didn't quite understand. I'm sorry.
I have to send you an email for starting?
I still don't understand.
So my main question is, I have some bugs. I want to be supported to LinuxBios.
Oh, okay.
I have some basic knowledge of how the hardware works. So how can I get started in making my system compatible with LinuxBios? How can, what should I need? Maybe an EEPROM programmer, maybe some...
Actually, the main thing you need is knowledge of the chipset. So I haven't used an EEPROM programmer since about 2001. We do all our programming on the motherboards, and a chipset guy pioneered this and told me it's safe. We actually unplug the flash part while the board is live, plug a new one in, and program it. The main thing you need to do is get on a mailing list and send us an LSPCI. That's always the first point, LSPCI, and then we can talk about whether it's possible. So
Thanks.
it'd be great to have you involved. Yeah. Yeah. Install LinuxBios? Okay, so the question is, how do you install LinuxBios? There's a couple ways you can go at this. It depends on how daring you are. I'd get on the mailing list to start and ask if anyone else has had experience with the motherboard you're using. And sometimes I just send people an image. Jordan Krause of AMD has built a utility called Build ROM, and Build ROM will allow you to basically lay out your motherboard, and if you say make, it pulls down the kernel it needs, it pulls down the LinuxBios, it builds the right version of LinuxBios for that motherboard, and when you're done, you've got an image that has a kernel and an NRD and the LinuxBios image, which you can just flash. But the mailing list is usually the best place to start to make sure you know what you're going to do. Not everybody wants Linux and Flash. Some people just want the grub-like loader. So it'd be good to talk to the mailing list and see what's possible. All right, thanks.